Let's start with a velocity versus time graph. And draw like this, and then like this. Those time intervals are supposed to be the same. We'll go ahead and put units there. Okay. So this is our velocity versus time graph. Initially, for the first 2 seconds, it's traveling at constant speed. This would be uniform motion. And then it changes and starts decreasing speed until it reaches 0 speed over the next second. Okay. Question is, what is the displacement as a function of time? How can I create the position versus time curve for this one? Okay, we'll have our same time intervals. We're going to find our position in meters. Okay, so we know that to go between it is delta x is the area under the curve. Okay, so we have to find the area under the curve. Okay, so we can do kind of a connect the dots type method. Let's think about how far has it gone in the first second. Okay, now remember that I can only find delta x. So we're going to go ahead and assume that x at t equals 0 is equal to 0, just to keep things simple. But remember, we have to consider that. We have to always think about that, because going from velocity to position, I don't know position, I only know displacement. So as long as I know, additionally, I know the initial position or the position at some time, then I can find position versus time. Okay, so knowing that we're starting at x equals 0, that means I know at t equals 0, I start at x equals 0. Now I'm going to add to it my displacement from 0, the area under this curve. So in 1 second, I've gone 1 meter per second. So the area of that curve is 1 meter per second. In fact, I'm going to write this out like this. This is 1 meter per second height times the base of 1 second. Okay. Now I want to write it out this way because if we look at the units here, we say area, and often area we think meters squared, or area is length squared. But we're not talking about a physical area, we're talking about an area on a graph. And this graph doesn't have dimensions of length times length, it's meters per second times time. So our area here is in units of 1 meter per second times seconds. The seconds cancel, I'm left with 1 meter. So this equals 1 meter. So this area under the curve, this graphical area, in this case, velocity versus time, is actually in units of meters, which is correct because that gives us a displacement. And so I know that at 1 second I've gone 1 meter. Okay. All right. Now before we continue on, let's think about, well, what happened at half a second? Well, at half a second I had gone the same speed, but half the time, which means I went a half meter. So I just plug in a half second here, and I'd get 1 times a half. I'd get a half meter. So at half a second, I'd get half a meter. I get there. What about at a quarter second? Well, that means I've got a quarter of the distance at the same speed. So I've got a quarter, 3/4, and you can see that creates this straight line. So given that during that time interval the velocity was constant, I should have a constant slope between 0 and that point. Okay, we can continue. We see that we continue for another second traveling at that, and so we can automatically say, oh, this slope's going to continue at a constant rate. So this is a constant slope all the way up to 2 seconds. Okay, and so that's equivalent to the addition of this area that's at a constant height as we tick along in time. But this one, what do we do here? Okay, now the velocity is changing, so this value over here is changing as my time increases. Okay, so thankfully I already know I'm right there to start at the 2 second mark for this portion of the motion. That's where I'm at 2 meters already. And so now I want to find the displacement as go another second. Okay, well, the area under this curve is a triangle. So the area here is 1/2 times base times height. So I got the 1 second times the height of that triangle is 1 meter per second. Okay, so over that next second, my displacement is going to be 1/2 meter. Okay, so instead of getting all the way up to 3 meters, I'm actually only going to get to 1/2 meter. 1/2 meter above where I started. Remember, it's delta x. And so, how did I get there? Well, with a changing velocity, I should have a changing slope. I only got 1/2 meter over a full second, where I was going a full meter per second. So the slope needs to go from a meter per second to 0. And so it looks like that. It's a curve. Starting at a non-zero value and going down to 0. And so this is the position as a function of time. We had to connect the curves. The curvature here is the same. That's tangential. And this was tangential with 0 because my final velocity is 0. So the slope there was tangential. That's how I finished this. And the slope there was tangential to what I knew. And I just had to connect that together. So that's how we could find the velocity as a function, or the position as a function of time from our velocity as a function of time graph.